welcome to Pre-Algebra Lesson 9-6, Find Probabilities of Compound Events. In this lesson, we'll be able to find the probability of a compound event. Let's start with solve and discuss it. Talia is playing a game in which she must choose option 1 or option 2 and then spin the game wheel, flip the coin, and roll the number cube labeled 1 through 6. Wow, a lot of things going on, right? At the same time. For her to win a prize, all the conditions listed under the chosen option must occur. Which option should Talia choose? Explain. So, we have spin the wheel, we have the dice, right? And then we have the coin, right? So option 1, the game wheel lands on S. Out of all these letters, and then option 2, and then the coin lands on tails, and then an even number is rolled, right? And then there's another option where the game wheel lands on Z, and then the coin lands on either side, and then the number 3 is rolled, right? So then either of them is not easy, but maybe there's a better probability out of these two options, right? So how do we know which one's better for her? That's when we use probabilities, right? So we have a compound event like this where there are different things happening at the same time with different number of outcomes, but then it must occur together at the same time, right? So how can you use what you know about sample spaces to choose the best option? So we have a large sample space in this case because we have a lot of different options, right, for each one. So we can think about different ways to write the sample spaces using the table or the lists or the tree, right? Writing the trees. So I think in this case, tree would be a good idea. So let's look at option 1. Option 1, out of all these letters, how many letters do we have? 1, 2, they're not in alphabetical order, so we want to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 15 different letters, and then 2 different outcomes for the coin, head or tail, right? And then 1 through 6, so 6 different outcomes. So 15 different outcomes and 2 different outcomes and 6 different outcomes, and if you multiply them, that would be the total number of outcomes we have. But let's look at option 1. The game wheel lands on S, so we need specifically S, and then we need instead of head, we need a tail, right? We have A, B, C, D, dot, 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 dot. We need a tail. And then we need even number. Not 1, but 2. Not 3, but 4. Not 5, but 6. Right? So either 2, 4, 6. So we have 3 different outcomes that is possible for option 1. So 3 winning combinations. And then, which is 3 winning combinations would be what? ST2, ST4, ST6. And then option 2, the game wheel lands on Z. So we have Z, we need to have Z, and then the coin lands on either side. So head could be possible, tail could be possible, but then we need specifically number 3. So instead of 1, 2, 4, 5, 6, we just need 3. And then also there's one possibility for the tail for this to be. So there are 2 different outcomes in this case, right? So 2 winning combinations. So which is ZH3 and ZT3. So if you just look at the coin, oh, the coin has to land on tails for option 1. Option 2, the coin can land on either side. So it looks like it could be a little bit misleading because option 2 looks like it has a greater possibility. But really, no. The number 3 has to be rolled, and that's just only one number. Here, you have an entire number set of even numbers, so you have 3 different numbers, right? So in this case, option 1 has one more winning combination. So which one would be a better choice for Talia? She should choose option 1, right? Because it's a better probability. So let's write that down. Talia should choose option 1 because there are 3 winning combinations, and option 2 only has 2 winning combinations. So option 1 has a better chance of winning compared to option 2. Okay, good. So this is why we need probability in real life. Let's look at focus on math practices. Suppose an option 3 was added to the game with the conditions that the game wheel lands on Q, the coin lands on either side, and an odd number is rolled. Should Talia change her choice to option 3? So is this a better option? How many winning combinations do we have for this option? Okay, so let's see. We for option 3, we should have Q and then either side, so head or tail, right? And then odd number. Ooh, that's a better option. 1, 3, or 5, right? 1, 2, 1, 3, or 5. 1, 3, or 5. So there are how many different winning combinations for this one? 1, 2, 3, 4, 5, 6. 6 different winning combinations. So this is a lot more than 2 winning and 3 winning combinations, right? It's double as much as option 1, right? So we have 6 winning combinations. So this is better. So let's write that down. How do we explain that in words, right? So should she change to option 3? Yes. The first condition is equally likely for all options because we're just choosing one letter. However, options 1 and 3 are equally likely to have a successful roll of a number cube, of the number cube. But the certain coin flip makes option 3 more likely to win. So choice 2 also has a certain coin flip, but a successful roll of the number cube is more likely in option 3. So option 3 has 6 winning combinations. Which is the greatest of them all. So option 3 would be the best one. Good. So we didn't even know option 3 existed. Maybe it just it was just added later on. But in this case, obviously option 3 would give you a better chance of winning. Okay, so in this lesson, let's think about this essential question. How can a model help find the probability of a compound event. Let's look at example 1. Find the probability of compound events using a table. Sadie has 1 ticket left at the school fair and she hasn't yet won a prize. She decides between 2 games. Which game should she play? So if you look at these 2 games, we have different probabilities for these games, and we want the game that will make her win, right? So does having more possible outcomes make it more likely or less likely that Sadie will win, right? So obviously if we have more outcomes that would be favorable for her, it'd be great. But if we have a big sample space and then a limited number of outcomes that we want, then obviously bigger sample space, bigger outcomes does not always mean a good one, right? So if we have too many outcomes total, that means we have a really big sample space, and that means less chance for a favorable outcome. So let's look at these steps to solve this problem. First, we can use a table. So remember, you can use a table to represent all the sample space. So for the first one, we have to flip to win. Flip 2 heads to win a prize. And then the second one, we're going to flip and spin. So flip a head and then spin blue to win a prize. So which one has a better probability, right? Obviously, for some people, it would be very obvious because you'll think, 50% and then 50%, that would be better than 50% and then 25%, right? But let's see how we can explain that using probability and logic, right? So first, you can use a table to determine the probability of winning a prize playing flip to win. So we can either have 2 heads or a head and tail, tail then head, and then 2 tails, right? There are 4 possible outcomes total. But there's one favorable outcome, which is head. So from all the different outcomes, the probability is 25%, 1/4. Okay, and then if we look at the second one, we have 2, 4, 6, 8 different outcomes, right? We have a bigger sample space. We have one favorable outcome, which is having the back and then spin blue, right? So blue and then head. Yeah, so head and blue. So I think they wrote the color first here. That's a little bit confusing, but that's okay. BH. So this is the favorable outcome we want here. HH is the favorable outcome we want here. So BH is the only favorable outcome we can have here. Out of all the bigger sample space, will give you less of a number, less of a fraction, 1/8, which is about 12.5%. So obviously 25% is a lot bigger than 12.5%. So the probability to win the first one is a lot greater than the second game. So she should use her last ticket to play flip to win because she has a better chance of winning, right? So this is something that will help you in games, right? Probability. So let's look at Try It. The designer of Flip and Spin creates a new game using a 5-section spinner. So now it's 5 instead of 4. It's shown how does the new spinner change the probability of winning a prize. So think about the situation. See if you can fill in the blank by yourself and answer to convince me by yourself. Pause the video and come back when you're ready for answers. Okay, are you ready for answers? All right, using the 5-section spinner, we know that using the coin and the 5-section spinner instead, the coin, the probability is getting the head. So head would be 50% chance. And the probability of getting a color from the 5 sections, spinning blue, would be 1 out of 5 possible outcomes. So altogether, you can multiply these fractions and get 1/10 as a total possibility because you need a head and you need a blue, a specific color, and a coin side out of 10 possible different combinations. So the probability of winning a prize for a 5-section spinner and a coin would be 1 over 10, or 10%. Is it more likely or less likely that they'll win a prize? So compared to 1 over 8, it is less likely, right? So it's less likely that a player would win a prize when using the 5-section spinner than when using the 4-section spinner, because there are more outcomes, but we still have one favorable outcome. So convince me, what generalization can you make about the number of sections of the spinner and the probability of winning a prize while playing the flip and spin game? So we see the pattern. We know one favorable outcome. So the more the possible outcomes are, the less likely it is, right? So as the number of sections increases, the probability of winning a prize decreases. It's true. So you want to find a game that has the least possible outcome with a favorable outcome. Okay, let's move on to example 2. Find the probability using a tree diagram. So what's the probability that a coin flip 3 times will land heads up exactly 2 times? So you can use a tree diagram in order to see all these possibilities. So if it's a head and a tail, right? So flip 1, you get a head. Flip 2, you'll get a head or tail as well. Flip 3, you'll get head or tail, depending on each flips, right? So there are different outcomes. You can have HHH, or HTH, or HTT, or HHT, right? HTH, HTT. So all these different outcomes in order. So the outcomes using the initials would be all these different things. And we want heads up exactly 2 times, and it doesn't matter which order there are. So it could be this, or that to get 2 heads, right? So we can have 3 different favorable outcomes for 1, 2, 3, 4, 5, 6, 7, 8 different total outcomes, right? So 3 out of 8 would be 37.5%. So sometimes we don't want exactly one favorable outcome. There may be more than one time that would happen. So you need to count how many times. Let's look at try. Is it more likely that a coin flip 3 times will land head up exactly once, or will land heads up exactly 2 twice? Explain using probability. So if you have a coin, you flip 3 times like this, and is it going to be more likely that it heads up exactly once, only 1 H, or heads up exactly 2, so 2H? So looking at all these outcomes, how many times do we have exactly 1 H? 1, 2, 3. How many times do we have exactly 2H? 1, 2, 3. So 3 out of 8 and 3 out of 8. So they're the same probability. So neither is more likely, right? So use probability to explain it. So pause the video and see if you can try explaining it. Come back when you are ready for answers. Okay, are you ready? I already told you the answer, that is neither, but can you explain it, right? So it's neither. Why? The probability, basically what I told you, the probability is the same, which is 3 over 8 or 37.5, because HHT, HTH, THH are the three different outcomes where you will have the heads up exactly twice, but you have HTT, THT, TTH, which are three different outcomes as well to get the heads up exactly once. So the probability of each event is 3/8, 37.5%, which is the same. Okay, let's look at example 3. Find the probability using an organized list. The names of all middle school students with perfect attendance are entered into a drawing for one of two tickets to a baseball game. This year, Angie, Phil, Mark, Carly, and Josie attended school every day. What is the probability that Mark's name will be drawn to win one of the two tickets? Ooh. Okay, so you can only apply you can only win when you have a perfect attendance, and this year we only have 1, 2, 3, 4, 5 people who have a perfect attendance. So, what is the probability that Mark's name will be drawn to win one of the two tickets, right? So they have 2 tickets. Yeah. So you can make a list of possible outcomes, right? Angie may win the first ticket, and then the next ticket would be the other people. If Phil wins the first ticket, you can have all the other ones like that. Mark, and then all the others. So you can use acronyms to simplify your outcomes, your list, and it's convenient that they all have different acronyms, right? So we have Angie and Phil, Angie and Mark, Angie and Carly, Angie and Josie, Phil and Angie, Phil and Mark, Phil and Carly, Phil and Josie, Mark and Angie, Mark and Phil, Mark and Carly, Mark and Josie. Yeah, so we're drawing 2 times. And what is the probability that Mark's name will be drawn to win one of the 2 tickets? So if Mark wins the first ticket, then that's it, right? We just want his name to be drawn once at least. So that's all a favorable outcome. But if other people's names are drawn first, we still have another chance to get his name drawn, right? So then this case, this case, this case, and this case, and all that case. So we have total of 4, 5, 6, 7, 8 favorable outcomes out of 4 times 5, 20. So 8 divided by 20 would be 40%. So 40% is a pretty high possibility. Yeah. Okay, so try it. Does Mark have a greater chance than Carly of winning the tickets to Carly? Explain using probability. Just by looking at our list. Our Carly, if it's a Carly, if Carly was the first ticket, we have this whole set, right? And then we have the other people's name drawn first, but there's still the same possibility that Carly's name would be drawn, right? So it's still 8 out of 20. So using probability, 8 out of 20 or 40% is still the same. So no, not really. Mark doesn't have a greater chance than Carly. They actually have the same probability. So we can say, based on the organized list, the probability is the same for both, which is 8 out of 20 or 40%. Okay, so that's basically it. Our key concept from this lesson is the probability of a compound event, right? And knowing that it could be represented by ratio of number of favorable outcomes to the total number of possible equally likely outcomes. So favorable outcomes versus the total outcomes, total possible. That's your probability. And you can use an organized list, a table, or tree diagram to determine the number of favorable outcomes and the total number of possible outcomes. Okay, so that was lesson 9-6, find probabilities of compound events. We can continue with the next lesson in the next video. Bye!